This lesson is locating the extrema of a function. And the extrema are the maxima and minima that we'll try to locate. Locating extrema is an important concept in mathematical analysis because extrema are the extreme values of a function, the points that are the highest and lowest locations on a graph. And for example, if we have a function that represents the profit of a company, it would be important to know where the profit is maximized or minimized. Or if we had a function representing the path of a ballistic, understanding where the height and distance is maximized can help us predict where it would land. When it comes to discussing the extreme values, we first must distinguish between a global, which is also known as an absolute extrema, and a local, which is known as a relative extrema. We'll begin talking about relative extrema. A relative extrema is a maximum or minimum value over a small interval of a function. A function may or may not possess relative extrema. We'll see some different examples and understand why. So to begin, here's a function, and this particular function does have some relative extrema. So the relative extrema are the points, for instance, right here. This is called a local minimum. So this is the smallest value over a small interval around this particular point. So this point, this minimum, is occurring where x is -3. So at around a small range of numbers around -3, that's the smallest value. It isn't the smallest value of the function overall, it's just the smallest over a small range. Similarly, we have another relative extrema right here. This would be a relative maximum, whereas this was a relative minimum. And likewise, we have another relative minimum at this position here. Now, we know enough about tangent lines to predict what the slope of a tangent line should look like at any particular point. And if you'll notice, at both the relative minimums and relative maximums, all of the tangent lines are horizontal. So what happens here is the first derivative is equal to 0. And that's a really good clue as to where relative extrema are going to occur. But that's not to say where they would always occur. So for instance, if I look at this particular point right here, it turns out the derivative at that particular point is 0. So the derivative, the slope of the tangent line, is equal to 0. But that's not a minimum or a maximum. So this is neither minimum or maximum. And in fact, this particular function has no relative extrema. And that can happen. So a function doesn't have to have relative extrema, but if it does, where the derivative is equal to 0 is generally a good indicator as to where that might occur. Here's another example. This one does have some relative extrema, and that's going to occur here and here, where we would have tangent lines that are 0. So we have a relative maximum and a relative minimum for this particular function, where the derivative is equal to 0. So, as I said, where the derivative is 0 is a really good indicator as to where relative extrema can occur. But it's also not the only place where relative extrema can occur. The derivative at this particular point is undefined. However, it is the smallest value over a small range of numbers, so it does qualify as a relative minimum. But the derivative is undefined there. So, over all these different cases, I think we can come up with a conclusion. Comparing these results, we can conclude that a function may have one point that is a relative extrema, it may have multiple points of relative extrema, or it may not have any relative extrema at all. But one thing that we can count on is that local extrema only occur when the first derivative is 0 or undefined. So these locations are called the critical values of the function. So to define a critical value, we say that the critical value of any function f is a point x equals c where the first derivative evaluated at c is equal to 0, or the first derivative evaluated at c is undefined. Let's work through an example and find all the potential values of f of x equals x to the fourth minus 8x squared, where relative extrema may occur. So to find the points where the relative extrema may occur, first thing that we need to do is find the derivative. So we need to find the derivative of our function. So f prime of x in this case, using the power rule, would be 4x cubed minus 16x. And then the next thing is set the derivative equal to 0 and solve. Now technically, we need to also consider points where the first derivative would be undefined. But undefined points occur where division by 0 can happen, square roots of negatives, things like that. And since we have a nice polynomial function, those aren't going to apply here. So I'm just going to set this derivative to 0 and solve that. So 0 equals 4x cubed minus 16x, or 0 equals, I can factor out the common factor of 4x, which would leave me x squared minus 4, or 0 equals 4x times x plus 2 times x minus 2 using the difference of squares formula, revealing three potential possibilities at x equals 0, x equals 2, and x equals negative 2. So we have three potential places where relative extrema may occur. And if we look at the graph of this function, what we'll see is exactly that. So here's x equals negative 2, and at x equals negative 2, we do have this first derivative equal to 0, because it's a horizontal tangent line. In that particular case, it's a relative minimum. We couldn't see that from the analytics, but we knew that it was either a minimum or a maximum. And at x equals 0, there would be a horizontal tangent line. So that's another position of possibility. And at x equals 2, right there was another horizontal tangent line, which could have indicated a minimum or maximum to us. And now that we can see the graph, we can clearly see that we have a minimum here, a maximum here, and a minimum here. And it might seem strange that 0 is our maximum, but most of what is happening with this graph is below the x-axis, so most of this graph is negative. And that's okay. 0 could be the highest overall, and that's fine. Now let's turn our attention to absolute extrema. So absolute extrema are the highest and lowest values on a function's entire domain, which could be a restricted interval and oftentimes is. If these values exist, there is generally only one absolute maximum and one absolute minimum. Sometimes they don't exist at all. Sometimes they're tied for first place. Absolute extrema can occur at relative extrema or at the endpoints of a restricted domain. Infinity is not a real number, and it cannot be used to label a maximum or minimum value. So keep that in mind. Let's take a look at some different examples. starting with this first graph. So this particular graph has a point of relative extrema. So this point of relative extrema is right here. This is a relative maximum because it's a location where the derivative is equal to 0. But it's also the absolute maximum. And the reason is it's the highest value over the entire domain. So it qualifies as a relative maximum, but it's also the absolute maximum overall. So of all the points in the entire function, that point has the largest y value. There's no absolute minimum. So there's no indication that this graph stops anywhere. And if it did, they would use a solid circle or a open circle indicating that. Oftentimes you'll see an arrow indicating that these things go on to infinity. If you don't see that, you just have to assume that's what's happening, because a lot of times the graphing software has trouble drawing those arrows in the right position anyway. So you just have to assume that if it doesn't stop, if it doesn't have an open circle or closed circle stopping the graph, that it goes on to infinity. And in this case, this would go to negative infinity, which means there's no value that is the absolute minimum value. So it only has an absolute maximum. This next example, this one neither has an absolute minimum or an absolute maximum, because the graph itself goes off to positive infinity in both directions. So this graph has no absolute extrema. Okay, whereas this one had no absolute minimum, this one has no absolute extrema at all. Part B has no absolute extrema at all. Alright, let's look at one that's on a restricted domain, because if we restrict our domain, then different things can start to happen. So for this particular graph, we do have an absolute maximum, and that's happening at a point that it happens to also be a relative maximum. Because as I said, absolute extrema can occur at at the end points of an interval or at relative extrema. So you find all your relative extrema and then find the endpoints of your interval. So here, the endpoints of my interval are this point and this point. What we're interested in comparing is not the x values, but actually the y values that are contained. So for instance, the y value for this one is about, I don't know, 1.75, let's say, just as an approximation. The y value for this looks like it's at 4. The y value of this point looks like it's at -2. So the one that is the largest overall is 4. The one that is the smallest overall is -2. So the absolute minimum is this point. And we're only comparing y values. Once you locate your relative extrema, you're no longer using derivatives. You're just looking at y values. All right, that was on a closed interval. Now let's do the same sort of idea, but put it on an open interval. All right, so this time I have a relative extrema here, and that is going to be my absolute minimum. It is the smallest value overall. Now, these other points, this one isn't even a contender because it's between my absolute minimum and this point up here. So it's not even a possibility for an absolute extrema one way or the other. This one up here, it looks like it's at about, let's say, 4.25. But the problem with that is this. If that open circle is at 4.25, then it's not included as part of the domain of this function. So 4.25 doesn't include in this set. It isn't included in this set. So 4.25 is not the absolute maximum. So this is not the absolute maximum because it doesn't exist on that set. So then you might be thinking, okay, well then it's just the next point down, which makes sense. It does make sense, but here's the problem. What is the next point down? We have 4.25. Let's just round it off to 4. What's the value right below 4? Is it 3.9? Well, no, because I can find a value that exists between 4 and 3.9. How about 3.91? Okay, well then you might be thinking, all right, how about 3.99? That's even closer to 4. That's true, but I can still find a value between 3.99 and 4. Any value that you come up with to call the value right below 4, I can find another value that's in between 4 and that value you've defined. So it may seem perplexing, but because this is on an open interval, there is no absolute maximum value. So this has an absolute minimum, but there is no absolute maximum. On a closed set, everything was fine because we included those endpoints. But when we don't include those endpoints, that's when problems start to occur. Right, let's look at some crazier ones. How about this? We have a discontinuity. Well, still, we're really only looking at the y values. So we can look at y values. This one here looks like that point has a y value of 1. This has a y value of about 2. Same here. They tie there, it looks like. So they still have the same y values. And that's all we're comparing. This one is at 3, but it's not part of the domain. So I can't use that as a maximum value. So here I do have an absolute minimum, and that's at that point, but there is no absolute maximum. All right, here's an example that has multiple absolute extrema. You should probably recognize this as a sine wave, but the thing is, here's a point of relative extrema, here's a point of relative extrema, here's another one, here's another one. All of these relative extrema occur at either 1 or -1. And so what's happening here is, I'll make that a little bit more highlighted. What's happening here is we have the same values of relative extrema over and over again. So this is a rare case where you have something that's tied for highest or tied for lowest. So in this case we do have multiple absolute minimum. Okay, which you could just call each one the absolute minimum. It doesn't make a difference. And then here we have multiple absolute maximums. All right, so it's a rare case, but it can occur, so I wanted to show you an example of when that might happen. But these examples combined together bring us to what's known as the extreme value theorem. And the extreme value theorem states that if f is a continuous function on a closed interval from a to b, then f has both an absolute maximum and an absolute minimum value on that interval. So as long as you restrict yourself to a closed interval like we did in C, you're guaranteed to have both the absolute maximum and the absolute minimum. All right, let's find the absolute extrema of the function f of x equals 2/5 of x to the 5th power minus 8/3 of x to the 3rd power on the interval from -3 to 1, and this is a closed interval. Okay, so absolute extrema can occur at the endpoints of your interval, and it can occur when relative extrema happen. So we need to collect all these different points and then do our test. Our test is very easy. All we have to do is plug these values into the function, see which one is highest and which one's lowest. But we have to collect all those points first. So first thing let's get is the location of critical values. Because critical values is where relative extrema could possibly happen. So these critical values, we would take our first derivative, so 2/5 of x to the 5th power would be 2/5 of 5x to the 4th, and then minus 8/3 of 3x squared, which gives me 2x to the 4th minus 8x squared. And I'm going to set this equal to 0 and solve it. There aren't going to be any places where I could have division by 0 or anything like that, so just set it to 0. 2x squared factored out of this polynomial leaves me x squared minus 4. So I end up with the potential locations, my critical numbers are x equals 0, x equals 2, and x equals -2. And the 0 comes from where x squared is just 0, and the 0 for x squared minus 4, the potential there is positive or -2. Now, the next thing that I want to check is making sure all of these values appear on my interval. So my interval is from -3 to +1. So +2 is actually not on this interval. So we don't have to use it as a test value. So we can exclude it. So my test values are just different x values. 0 and -2. Those are potential places on the interval that are relative extrema. And absolute maximums and absolute minimums can occur at relative extrema or at the endpoints of the interval, so I'm going to test those values as well. But my test is just simply to plug these into the function f of x and see what value I get back out. So let me get my calculator, and what I'm going to do to help speed this up is use a table, just like we learned how to do with the limits. So I'm going to put my function, which is 2/5, and, oops, not 25, 2/5. If you're unsure as to whether a fraction needs to be in parentheses or not, it doesn't hurt to go ahead and put it in parentheses. And then that's multiplied by x to the 5th. Then it's plus, whoops, nope, it's minus 8/3 x to the 3rd power. And I will just check and make sure my table settings are proper. All I need is the independent variable set to ask, the dependent variable set to auto. And we'll go into the table, so second and graph. And it looks like I already have some points in here that are being evaluated. I'll just get rid of those by hitting delete. I want to evaluate my function at 0, at -2, at -3, and 1. So f of 0 is 0. F of -2 is 8.53. F of -3 is -25.2. And f of 1 is -2.27. So, looking at these y values, what I can determine is the biggest overall is 8.53. This is my absolute maximum on this interval. So of all the y values of my function, this is the largest on this interval. Then also the minimum value is this -25.2. So that is my absolute minimum value on the interval. So let's take a look at the function, see the interval that we're concerned with, and just make sure this all works out the way we expect it to. Okay, here's a graph of my function, and it's not the full function. If I show the original curve, that's the entire function. And so we're only looking at a portion of this, and that portion is from -3 on the x over to +1 on the y. So from here over to here, -3 to +1. When I show the entire curve, what you can see is that I came up with 3 relative extrema. So here was one potential relative extrema at -2. Here was another potential relative extrema at 0. And another relative extrema down here at +2. But if you'll recall, we threw that out because it wasn't on the interval that we were concerned with. So I'm going to get rid of the whole function and just look at the portions that we are concerned with here. So let's get rid of that. What I'm looking for is the largest value overall and the smallest value overall. And as we said, that can occur at the endpoints of an interval or any relative extrema. So if I move, whoops, get that back there where I want it. If I have these values to search through, one of the relative extrema was at -2, and I'll try to get as close as I can to -2. And what we saw is the y value there was about 8.53. And that's meshing up with what we have here. So we're just looking at y values when we have the relative extrema. The other relative extrema was here, which was 0, and the y value was 0. Then we had to test the endpoints of our interval. So one endpoint was at +1, which is at a y value of -2.27 approximately. And the other is the y value of -3, and it had or the x value of -3, which had a y value of -25.2. So when we are searching for absolute extrema, we are looking for the absolute largest value on the function's domain and the absolute smallest value on the function's domain. And as long as we're on a exist. In this case, this is my lowest overall, and this is my highest overall. But if I allowed the entire domain to exist, so this is a non-restricted interval, then there wouldn't be an absolute minimum or an absolute maximum because the function goes off to infinity, both in the positive direction and the negative direction. So as the theorem states, the extreme value theorem that is, this only occurs if you're on a restricted closed domain. Find the absolute extrema of f of x equals 9/2 x to the 2/3 minus 3x on the interval from -1 to 2. So we need to find first any critical numbers. Sometimes we call them critical numbers, sometimes we say critical values. We mean the same thing, so depending on what the book says. Critical numbers here, these will occur where the first derivative is equal to 0. So our first job is to determine what the first derivative is. All right, a little bit trickier, but we still can use the power rule. So it's 9/2 times, we bring the original exponent down, so times 2/3, x to the 2/3 minus 1. We subtract 1 from the exponent. So this is going to be -1/3 power. And then 3x, its derivative would just be 3. So cleaning this up, 2's can cancel, 3 can go into 9 3 times. So I have 3 over the square root, the cube root of x minus 3. Now, if I set that equal to 0, then I can come up with my potential critical numbers. So I set this equal to 0. First thing is, let's add 3 to both sides. So I have 3 equals 3 over the cube root of x. And then next what I'll do is multiply both sides by the cube root of x, just to get it out of the denominator. So 3 times the cube root of x is equal to 3. Divide both sides by 3. So now I have the cube root of x is equal to 1. And that's going to occur when x is equal to 1. Because if I cube both sides to get x by itself, so the cube root of x cubed cancels the cube and the cube root out, and then 1 cubed is just 1. So this happens when x is equal to 1. So that is a potential critical number, or a potential, that is a critical number, but a potential place where relative extrema could occur. But that's not the only that's not the only critical number. If you go back to this function right here, if you'll notice, if I put in x equals 0, I would get division by 0, and thus the derivative would be undefined there. Whoops, not equals, just undefined. So f prime of x is undefined. So my critical numbers are x equals 0 and x equals 1. So I have 2 critical numbers. And the reason I picked this example is because it has a critical number where the first derivative is undefined. It honestly doesn't happen often in problems, but you do have to be aware of the possibility and keep in mind that it could occur. Most of the time, it's where division by 0 would happen. So it's usually not a lot of algebra to solve to figure that out. You just have to know what x value would go into a denominator that would result in division by 0. But you do need to make sure you are looking for those sorts of things. Now, that gives us all of our test values. So the test that we're going to do is take all of our x values that could be the location of absolute extrema. So 0 and 1 are the critical numbers, which could be relative extrema. But we also need to check the endpoints of our interval, which could be -1 and 2. And so I just need to plug each of these values into my calculator in order to figure out what their y values are. So I'll put it in for y1. So I have 9/2 x to the 2/3 power. And you really can type in x raised to the, you have to have parentheses, but then do 2/3, that's fine, minus 3x. And then, once that's done, my table's already set from the previous example, so I'm just going to go into the table itself, and I can start plugging in the values that are of interest here. So 0 and 1, -1, and 2. Make sure you double check at some point the critical numbers that you come up with happen to be on the interval. I didn't specify it here, but they are on this interval, so I don't want to exclude them. But double check that at some point. So it looks like I've got f of 0 is 0, f of 1 is 1.5, f of -1 is 7.5, and f of 2 is 1.14. And that's enough for me to be able to determine that this is the location of the absolute maximum, and this 0 is the absolute minimum. Now, in terms of answering, sometimes the question is worded so that they want the location of where the absolute maximum occurs. So that would be the x value that they want. Sometimes they ask for the absolute maximum, and they generally want the y value in that case. Sometimes they say find the point where the absolute maximum occurs. Then they want the coordinate pair -1, 7.5. So just be careful for the wording of the problem how to answer the final answer. Now, if we look at the graph of this, I think it'll make sense with the problem as to how this is working out. I do want you to see it, however, because it is a different type of graph that you may not have seen before. And what you can tell here is we do in fact have a relative extrema right here at +1. That's a point where the first derivative would be 0. And then down here we also had a critical number, and this is where the first derivative is undefined at 0. That was a potential point for local minimum or maximum. The interval itself was restricted from -1 to 2. Let me double check that. Yeah, -1 to 2. So wherever f of -1 is, and wherever f of 2 is, these are also potential candidates to be the highest and lowest overall. Now, I don't think I did a very good job of drawing that line straight up from -1, because it was the highest overall and it was 7.5. I've got it more at like 6, but I think if I did it a bit more straight, I would have gotten the 7.5. So try it again. So anyway, so this is at about 7.5, and that was my highest overall. Then this was at 0. That was the lowest overall for the entire domain, because we're not looking at the whole function. We're only looking at this portion that I'll sketch in red. So from here to here, that point at 0 was the lowest overall, and at 7.5 that was the highest overall. So that's what we're looking for. We're comparing y values with absolute extrema.